Good morning, everyone. My name's Ian Wilson. I have a trade background. I'm not a university trained person, so you won't see a lot of graphs and charts and things from me. The presentation I intend to do now is the progression of CO2 system design over 3 projects that we as contractors did for one particular customer. Meyer Imports are a specialty importer of high quality European foodstuffs. They have a coalition with the Danish the Danish dairy industry, and they import a lot of butter and a lot of cheese and a lot of different things. Import and then distribute through Coles and Woolworths and a whole lot of specialty people. And they were trading out of a business over near the airport, and old Fred Meyer bought a site, and he outgrew it and bought the one next door, and he outgrew it and bought the 2 next door, and outgrew it until he owned half the street. And he had forklifts running back and forwards, and the place was chaotic, and they'd completely outgrown it. And they decided that they needed to move to a new site and consolidate the whole thing into one big freezer, one big cool room and so on. And they wanted to move beyond little higgledy-piggledy plants that they struggled to keep running to go to a new design. And we tendered the job. We won the job largely on the strength of energy savings that we proposed. We've subsequently done 2 more projects, each sort of 2 years apart, so I'd like to take you through those jobs to show you how the jobs evolved. The first one was in 2011 and was basically a CO2 freezer room with an R134A cascade arrangement, and then cool room through an R134A. And we'd already guaranteed energy savings of 25% over their 404A solution that they were currently going with. That technology is, maths has proven a long time ago. So they're over at Botany. They took a lease out on a large site that had a post-tension floor, so we weren't allowed to cut into the floor or anything. It's a freezer room, so they needed subfloor heating, and they wanted basically a green credential and a lower energy bill. So we came up with a glycol underfloor heating system that would be heated by heat recovered from the R134A package. We used warm glycol to do the defrosting of the system, which is also recovered from the discharge of the 134A systems. The cool rooms were basically just a straight R134A system, as Meyers at this stage, while happy to deal with us, they didn't give us a blank checkbook. And we used the Danfoss system to control the whole thing and give them real-time reporting. So the floor heating there, you can see that's a nylon pipe. There's about 2 kilometres of tube there. We take heat out of the discharge, we heat that glycol up to 50 degrees to do the defrosting of the evaporators, and then we heat 12 degree glycol off the 50 degree glycol and pump it through the floor to stop the subfloor from freezing and destroying the floor. Interesting, this floor, had they gone ahead with the electric defrost that was originally proposed by other contractors, would have cost $30,000 a year to run the heaters in the floor alone. No one ever says how much is it going to cost to run the floor. They're always thinking about the compressors and the fans. The floor can cost as much as all of your fans put together times 2. Incidentally, that floor costs about $400 a year to run a little pump. So there's the refrigeration plant for the freezer. You can see on the right hand side is the low temperature CO2 machine, and then it's directly coupled to an R134A machine that's taking heat from the CO2 and getting rid of it out through an air-cooled condenser outside. There's the low temp machine, and then the cool room machine. As you can see, this is all pretty standard stuff you would have seen in a supermarket at that time in 2011. We did what we could to reduce the amount of gas in the things. You can see there's a drop leg at the bottom of the vessel so that we don't have to put as much refrigerant in it, because if you can reduce the volume, there's less to leak. But it was still of its time. You know, there's nothing too exciting there. So the glycol system itself recovers heat from the discharge of the R134A system. A pump pumps it out of the glycol tank, puts it through the heat exchanger and back into the tank. We get it up to 50 degrees, and then on demand we start the delivery pump, and the particular evaporator needing to be defrosted turns the fans off. We open up a solenoid and pump 50-degree glycol through dedicated tubes in the evaporator, and that affects the defrost. The advantage of this system is that it's only 50 degrees, so at the end of the defrost, instead of electric heaters vaporising water which then floats back into the room to become ice again, all the water goes down the drain. The other thing is, at 50 degrees, it's not spewing heat into the room during the defrost. There's much less after defrost heat load. You can see at the top the little heat exchanger where we heat up the floor heat using the defrost system heat. So stage one basically was a fairly conventional thing for its time, with CO2 and 134A for the freezer, and then 134A for the rest, but the glycol systems help increase the energy efficiency quite a bit. I will also mention the 25% gain over the alternative sort of HFC technology at the time, and we won the ARBS award for the project of the year for that job. 2 years later, they'd outstripped that building and they needed to go again. So they basically built another freezer and another cool room and another loadout of exactly the same size. Same solution for the floor heating, but this time they gave us a bit more money, they had a bit more trust in us, and they decided they wanted to go to an all CO2 solution, which I'd mentioned a couple of years earlier, but they weren't that trusting at that time. So we went to a transcritical CO2 system, taking heat out of a subcritical CO2 system for the freezer, so a cascade arrangement, and then a subcritical for the chiller and the loadout. We hold a patent for a CO2 system that basically overcomes one of the problems with CO2, and that is that a transcritical system is very inefficient as the ambient temperature where you're trying to reject your heat to rises. So if the thing has to run in supercritical mode, so above 31 degrees, the energy efficiency takes a nosedive and the power usage goes way up. So we came up with an idea of cooling the refrigerant coming out of the gas cooler with a secondary system in hot weather, and that secondary system's turned off for most of the year. That allowed us to run the system as a subcritical system all year round. But there are some complications because we're talking about much higher pressure. So we looked at what was done overseas, because Sainsburys and different people had already done transcritical CO2 cascaded to subcritical. And when we looked at what they did, they just put a massive number of units out there and put a lot more capacity in than needed to cope with the real hot days. The problem is that in the UK, the really hot days are 35, not 45. And they're very few and far between. A heat wave over there goes for a week, and it's not a heat wave that we would understand. So what we did was we took our standard cascade system, and if you can see over on the far side of the slide is the low temp, and on this side of the slide is the medium temp. All of the heat goes to the medium temp, goes up to the gas cooler and comes back down. That'll work in the cool weather, but in the hot weather, the energy efficiency will be half of what it is on a cool day. So there's the one graph that I will show you, which is a comparison of the energy efficiency of R134A compared to CO2. As you can see, the blue line is fairly level, and as the condensing temperature rises over here on the 47 degree end of town, the energy efficiency of the 134A falls away, but nothing like the fall in the CO2 system. So we needed to keep the condensing temperature of the refrigerants as high as possible. The really interesting thing about this slide is that the manufacturers will allow you to select an R134A compressor at 20 degree condensing. The reality is though, it's very, very difficult to get it to work because there's not enough pressure difference to drive the gas around the system. And the first thing the service mechanic's going to do when he turns up is crank up the condensing temperature to 40 degrees where it works beautifully. So you don't have to compare it to a 16 degree condensing temperature because it's never going to work there. You've got to compare it to a 40 degree temperature, and the CO2 is already in front of it as soon as you get to what actually happens in the field. So to keep our CO2 system cool, we basically added in a plate heat exchanger on the outlet of the heat rejection condenser, and we put a second cooling system on that, so that on a hot day this second cooling system turns on. We cool the CO2 coming out of the condenser to make the plant think that it's a cold day. We maintain the energy efficiency, albeit by burning some extra energy to run this chiller, but the chiller's running at a much higher suction pressure, so it in itself is much more energy efficient. And the chiller looked like that. At the bottom you can see a twin screw compressor R1340 screw chiller. Probably not the most energy efficient way of doing this, but it was what the budget that Meyer's gave us would allow for. So there's a 7,000 litre chill water tank. The chiller pumps the water out of the tank through the plate heat exchangers and back into the tank, and it might only run the compressors for 5 minutes an hour on a 30-degree day, because it's sized to work on a 45-degree day, and every time I drop the condensing temperature by 1 degree, I take 4% of the load off the chiller. So there's the CO2 system. That's running a 120 kilowatt freezer on the right-hand side with the low temp package. The 3 compressors on the right of the 6 compressor package are high stage for the freezer, and the other 3 compressors are doing 180 kilowatts of cool room and load out. So there's the transcritical system. You can see it's not that complicated. There aren't that many pipes. You can make this as complicated or as simple as you want. So there's the transcritical flow diagram. If you follow one of those little balls around, it'll probably hypnotise you, and I'll be able to sell you a lot more, so that'd probably work all right. But the purpose of this is, that's virtually all the pipes there are. There's some little safety lines running off that are 3/8 inch, but that's it. There isn't any more. So these things don't have to be massively complicated. There's the low temp package. In this case, we were heating the glycol off the low temperature package and not the high temperature package. That means that heat doesn't go to the high stage, so we make a 20 kilowatt saving on the high stage for the entire life of the project. So there's another flow diagram, which I won't worry about too much because we're pressed for time. Glycol tank, and then a summary of stage 2. So we had a transcritical high stage, a subcritical low stage, and a water chiller to make sure the thing never ran supercritical. We had the same glycol defrost system, but this time heated from a less expensive source, but we still had a R1340 screw chiller to economise the whole thing. So the final project we finished at the end of last year. This one's in Melbourne. I should mention that that previous stage 2 plant is recording about 25% better performance than the stage 1 plant. When we went to this plant, Meyers were much more accommodating with the budget and much more trusting, and basically let us do whatever we wanted to do within reason. So the plant is quite similar to the one in Sydney, with the exception that the gas coolers now went to a V block with water sprays. So I can, when on a hot day, I can spray water onto the side of the coils, and that stops the chiller coming on for a little bit longer. It might go another 5 degrees hotter before I have to run extra power through the chillers. The chillers now are there's 2 little chillers there, with, you can see the on the right hand side of the dry cooler. They're now an ammonia critical charge chiller. The machines are about the size of a big wardrobe. It has a single bits of compressor in it with a VSD. It's doing about 170 kilowatts of cooling with a COP of 8:1, which is pretty good, and it has 5 kilograms of ammonia in it. It's sitting outside, so if it dumped the entire gas charge, by the time it got 500 metres away, not too many people are going to know about it. The other thing we did was we took out a patent on a floor heating system. So we've got the same basic starting point under the floor, but instead of heating the glycol with the heat from the discharge, we're now taking heat from the liquid line. So if I take the refrigerant to take all the heat I can out of it in the condenser, whatever temperature I get now is what I'm stuck with. And there are losses in that the colder it is, the more energy efficient the plant will be. So we started to scavenge heat out of the liquid line to cool the floor. So now we've gone from a situation in stage 1 where we potentially were paying 30 grand a year to run the floor. We got that to $400. By subcooling the liquid, we're getting about 1% better energy efficiency across the whole plant, and it's now saving money or paying us to heat the floor. So our summary of stage 3, basically the same CO2 system with our 2 packages cascaded together, but now the cool rooms are on a separate CO2 package because the scale of the place was bigger. We've gone to an ammonia chiller instead of a freon chiller, which has nearly 3 times the COP. Gas coolers with EC fans and water sprays to drag some more energy efficiency into the process. We haven't had the thing running long enough to know, but without it being in Melbourne where it's colder and it'll behave better anyway, just this plant compared to the other plants, had they been in the same location, we're expecting sort of 5 to 10% gain again over the previous effort. So the conclusion from all this is that multiple small improvements provided a significant COP gain by the time we got to the last plant, but it is a more complex thing. There are more parts. It's quite interconnected, and it was more expensive to install. We probably went up in 10% increments across the 3 projects per square metre of ground, if you like, refrigerated. It definitely way outperforms a chemical refrigeration plant, but it also costs significantly more, but it will pay back. And the last thing is, and it's very important, the control system is where you have your dramas. You don't have problems with the compressors, you don't have problems blowing relief valves if the control system is right. The control system has to look at the trends that are happening in the plant, and it has to act before you have a problem because it's trending towards a problem. So you've got to put a lot of thought into it, and that is all you'll get from me.